Here we see a pictorial representation of the classification of the various study designs that we have in epidemiology. So broadly speaking, they are divided into observational and experimental or interventional designs. And under the observational designs, we have those that are descriptive and those that are analytic. And under experimental designs, we have randomized controlled trials, field trials, and community trials. Again, this table shows the various classification and the alternate names for the various study designs. If you learn about different study designs and the advantages and disadvantages, you are in a better position to interpret and evaluate the results from various research. Now we'll move over to cross-sectional studies. These are yet another type of observational study design. They are one of the four types of observational study designs, and like cohort studies, cross-sectional studies conceptually begin with the population base within which the occurrence of disease or health outcome and sometimes the simultaneous occurrence of the exposure will be studied. For example, the population could be all individuals currently living in Idaho Falls, or it could be all children aged 5 to 6 currently attending kindergarten in Pocatello, or it could be all taxi drivers currently working in Boise. A key aspect of a cross-sectional study is that the exposure and the outcome are assessed at the same point in time within the specified study population. If you conducted a cross-sectional study in the year 2020, you would first define your study population, for example, all adolescents in high schools in the city of Boise, Idaho. You could then survey all the high school students at school and ask them about their exposure to traffic pollution, for example, how close they live to heavily used roads. At the same time, you could also ask them if they currently had asthma or asthma-like symptoms. In this example, you obtained the information about both their exposure, which is traffic-related air pollution, and their health outcome, asthma, at one point in time. This is in contrast to the cohort study in which you start with assessing the presence of the exposure and then ascertaining the disease or outcome at a later date. The cross-sectional study design is also different from the case control study, which, as you might remember, starts with selected cases and controls and then looks back at exposures in the past. An easy way to think of a cross-sectional study design is as a snapshot of an exposure and the health outcome at one point in time. Here's an example. Among all individuals living in the United States, what is the prevalence of HIV infection? We can also apply the cross-sectional study design to the topic of distracting driving by looking at a study done by Vera Lopez et al. In the year 2013. Using a mobile phone for either talking or texting while driving a car can lead to traffic accidents. The study took place in 2011 and 2012 in Mexico. Mexico, like many countries, has a public health problem with regards to high rates of deaths from traffic accidents. Several municipalities have passed laws restricting mobile phone use while driving. The researchers selected 3 cities in Mexico. Their goal was to measure the prevalence of talking and texting on mobile phones among drivers in the 3 cities. A sample of 3% of all intersections with functioning traffic lights in all 3 cities was randomly selected. With this sampling method, 7,940 drivers and their vehicles were observed from 2011 to 2012. The overall prevalence of mobile phone use while driving was 10.8%. Now we will discuss the numerator and denominator of the prevalence measure used in cross-sectional studies. Cross-sectional studies are often used to describe the occurrence of a health outcome or exposure in the population. The measure used to describe this occurrence is prevalence. For the numerator, you will include all existing cases of the health outcome or disease in the population group, that is the prevalent cases, while for the denominator, you include all existing persons in the study population or among study participants, including both prevalent cases and non-cases. There are several ways in which cross-sectional studies may be used. Some cross-sectional studies characterize the prevalence of a health outcome or disease in a specified population in a defined period of time. Other cross-sectional studies obtain data on the prevalence of the exposure as well as the health outcomes or disease for the purpose of examining the association between these 2 variables. For example, is smoking among adolescents related to smoking in parents? Now let's look at how to conduct a cross-sectional study. Under steady-state conditions, prevalence equals rate times average duration of the disease or health outcome. There are some limitations of cross-sectional studies. For instance, the prevalence is influenced by the rate and duration of the health outcome. For example, people who survive longer with a health outcome or disease will be more likely to be counted in the numerator of a prevalence proportion. Short-term survivors are not as likely to be counted as they are by definition around for a shorter time. Sometimes there can be issues with interpreting cross-sectional studies. Antecedent consequence bias affects cross-sectional studies and case control studies, but not cohort studies. In cohort studies, persons are selected for study because they're exposed or not exposed while they are still at risk and thus disease-free. For example, if you are investigating diet and arthritis, in a cohort study, we obtain data on diet at baseline because before any of the study subjects have evidence of arthritis. In a cross-sectional study, we ascertain dietary patterns at the same time as we obtain data on the presence or absence of arthritis. Thus, we cannot be sure that the exposure preceded the disease as they are both ascertained at the same time. So, what are cross-sectional studies used for? They are widely used to estimate the occurrence of risk factors, exposures, or health outcomes in the population. For example, a study to look at the prevalence of elevated blood lead in toddlers or the prevalence of asthma in children. National examples of cross-sectional studies of great importance are the decennial census, the National Health and Nutrition Examination Survey, or the prevalence of HIV-positive antibodies in military recruits. Opinion polls and political polls are basically cross-sectional studies. Surveillance of changes in smoking habits or other behavioral risk factors are sequential cross-sectional studies. Similarly, surveillance of long-lasting diseases such as AIDS are cross-sectional studies. The most important thing to remember about cross-sectional study design is that it's a snapshot at one point in time in which you measure both the exposure and the health outcome at the same time. We'll move over to ecologic studies. Ecologic studies make up another category of observational study designs. The key point about an ecologic study design to remember is that either the exposure or the health outcome or both are measured at a group or population level. In each of the observational study designs we've covered so far, generally, exposure data and health outcome data are collected from each study participant. In contrast, you can also make measurements at a larger group level. Generally, ecologic studies use group level measurements. For example, the exposure measurement could be yearly average air pollutant concentrations in 5 different cities. Sometimes the health outcome occurrence, proportions or rates is only known at a group level. For example, the yearly mortality or death rate from chronic lung disease in these same cities with measured air pollution levels. Group level data averages the exposure of the group, not individuals, but individual level data provides information on the exposure of each individual. With group level data, we only know the health outcome of the entire group. We don't know the exposure of individuals who became diseased and those who did not. But with individual level data, we are able to link individual exposures to those who became diseased and those who did not. Linking individual exposures is a critical difference to note between individual and group level data. This leads us to the concept of ecologic fallacy, the major limitation of an ecologic study design. Ecologic fallacy means concluding that an association between the exposure and the health outcome at a group level is true at an individual level, when this may not be true. The reason for this fallacy is that we do not know the length between exposure and the health outcome among individuals within each group. That is, we don't know the number of diseased persons who were exposed or non-exposed in the high exposure group or in the low exposure group. What we find at a group level may not hold in an individual level. Let's consider the hypothetical example that air pollution is higher in California than in Idaho, but mortality from lung cancer is lower in California than in Idaho. we might come to the fallacious conclusion that air pollution protects against lung disease deaths. The explanation might be that persons dying of lung disease in Idaho may have moved from high air pollution cities. We don't know the cumulative exposures of cases and non-cases in either state. Consider this example of an ecologic study question. Is the ranking of cities by air pollution levels correlated with the ranking of cities by mortality from cardiovascular disease, adjusting for differences in average age, percent below poverty level, and occupation? Note that in this example, there are no data at the individual level, allowing us to link individual exposure to air pollution with outcomes such as cardiovascular disease mortality. Now we will discuss advantages of the ecologic study design. Group level data on exposure and health outcomes are often publicly available in state and national databases, such as census data, mortality, and cancer registries. So ecologic studies have lower cost and are convenient. Ecologic studies are useful for evaluating the impact of community level interventions, for example, fluoridation of water, seat belt laws, mass media campaigns, etc. We can compare outcomes at a community level before and after the intervention. In the United States and many other countries, data are regularly obtained on air quality, water quality, and weather conditions, the size of the population, and the status of the economy and the health of the population. For example, the United States Environmental Protection Agency collects air pollution data at selected locations all around the country using the National Air Quality Monitoring Network. These monitors collect air pollution data at the group level. In contrast, to collect individual level air pollution exposure data, a person will need to wear an exposure monitor. Another advantage of ecologic study is that this study design can maximize exposure differences between communities where minimal within community differences render individual studies impractical, whereas exposures may differ substantially between communities, such as cities, states, or countries. Ecologic studies are also useful for studying the effects of short-term variations in exposures within the same community, for example, temperature and mortality. Examples of small exposure differences within a community, but large between community differences, include quality of drinking water, concentration of certain air pollutants such as ozone and fine particles, average fat content of diet, larger differences between countries than between individuals within the same city of a country, or cumulative exposure to sunlight where there are larger differences by latitude, north-south of residence, than among individuals within the same latitude. Now we discuss limitations of the ecologic study design. We have already discussed the ecologic fallacy. Ecologic fallacy refers to concluding that association at a group or aggregate level are true at the individual level when that might not be the case. Another limitation of ecologic studies is that we cannot be confident that exposure preceded outcome. Lastly, another limitation of ecologic studies is that we do not know what happened to individual people. Thus, migration into and out of communities can bias the interpretation of ecologic studies. It's important to remember that in an ecologic study, either the exposure or the health outcome or both are measured at a group level. One example to help you remember this is the example of air pollution that is measured at a central site and is used to determine what the exposures are for a population within a 10-mile radius, for example. That's an example of an exposure that's measured at a group level.